Hey y'all, today we are going to start a new unit which is going to follow directly from our last unit. So in our last unit we looked at several different methods on how we could solve quadratic equations, and one of those methods was to graph the related function and identify the x-intercepts. Well, in this unit what we are going to look at is how to actually graph quadratic functions without the use of the calculator. So before, really what we did was we just generated a list of points and just plotted those points and just kind of connect the dots. And that will still work, but it would be nice if we had a better understanding of how the parameters in the equation actually affect the graph. So that's what we're going to look at over the course of the next few lessons. Today we are really just going to look at how the leading coefficient and the constant affect the graph. So let's jump right into it. So today we'll be looking at these quadratic functions where we're missing that b term. So notice here, like we've got, either the b and the c are missing or just the b is missing. Overall, we're going to be looking at the effects of a and c on the graph. We'll look at the effects of b next time. Okay, so this bx you'll notice is missing, and that is because for today at least, this b value is always going to equal 0. Okay, so for all the examples today, we're looking at just when b is 0. We may have solved equations like this using the square roots last time, but for right now, we're going to just sort of ignore the b, and we're going to see how do we graph quadratic functions when b is 0. So before, what we did was we generated a table and just tried to plot the points and go from there. So let's just refresh ourselves with what the parent quadratic function is. So the parent quadratic function is going to be sort of your baseline function, and that is when y, or f of x, equals x squared. So when a is 1 and b and c are both 0, you have what is known as the parent quadratic function. So in the parent quadratic function, your input is simply squared to give you your output. So like for example, -3 squared is 9, -2 squared is 4, and so forth. Let me just fill out this table real quick for you. -2 squared is 4, -1 squared is 1, 0 squared is obviously 0. And then if you square the positive versions of those numbers, you get the same thing. So you get this nice little symmetrical behavior. We saw in the last unit that when we graph parabolas that they are symmetrical. So we're kind of expecting to see that kind of behavior play itself out in the graph and in the table as well. So let's just wrap this up real quick. So we get this nice little, this table of values where we're just squaring the inputs. Now, when we graph it, there are a couple of important characteristics that the graph has. First of all, the graph itself is called a parabola. Okay, so the name of the graph, the shape of the graph is called a parabola. Okay, so just wanted to make a note of that, so that when I say parabola, I'm just talking about this particular U shape of the graph. So when we graphed linear functions, for instance, we called that shape a line. Okay, when we graph quadratic functions, we call that shape a parabola. Now, the parabola is symmetrical, and that line, which is sort of like what separates the left half from the right half, is called the axis of symmetry. And I'll show you how to calculate that a little bit later, if I can spell it. But anyway, so that's the axis of symmetry, okay? And this point right here where the slope changes from a negative slope to a positive slope is called the vertex. So if you've have any geometry background, you may have heard this word vertex before, and the context is typically given to, like, if you've got a shape, the vertex is typically like the corner of the shape. So like if you have a rectangle, it's got 4 vertices, 4 corners. Really what's going on with this name is that it's when the slope of the object changes. So you have this sort of corner. It's not really a sharp corner like you would have on a rectangle, but it's still kind of playing the same role of the slope changing from negative to positive. So, so this point right here is the vertex. So we've got a point which is called a vertex. Let me zoom in a little bit here so I can draw a little bit more accurately. But we've got this point right here called the vertex, and it is a coordinate. Okay, so when the question is asking what's the vertex, we want to write it as a coordinate pair. And then we've also got this line called the axis of symmetry, which is the line that actually goes straight through the vertex. Okay, and it is a line, so the way you describe lines mathematically is with an equation. So your axis of symmetry is always going to be something like x equals and some number. The vertex is going to be just a pair of coordinates. So, okay, so we've got the axis of symmetry, we've got the vertex. Let's define some of these points, or some of these items a little bit more clearly. The lowest point on the parabola is called the vertex. Now, it is possible for that to be the highest point. Okay, so I want you to just kind of imagine in your mind what might have to happen in order for the vertex to be the highest point. So the lowest point on the parabola, or the highest point, is called the vertex. The vertical line that divides the parabola into two symmetric parts is called the axis of symmetry. Now, what is always true is that this axis of symmetry, because it's sort of cutting the parabola in half, is that it always will pass through the vertex. So the vertex and the axis of symmetry essentially always have the same x value. So if you can find the x value for one, you have the x value for both of them, because it's always going to pass through that point. So just to kind of get used to that terminology, let's take a look at a couple graphs here and see if we can identify what they are. I'm going to throw in some domain and range. Okay, we haven't really talked about domain and range in quite some time, so I'm going to kind of bring it back. Remember that domain is referring to the x values, and the range is referring to the possible y values. So when we start talking about that, I'll try to clarify a little bit what I mean. So let's talk about the vertex. We need to find the vertex. We need to find the axis of symmetry. We're going to discuss the, I don't know why I have so much trouble spelling this one. Symmetry. Now I'm looking at it, I don't even. Okay, so domain and range. Okay, so we want to find these four things. In fact, let me give myself a little bit more space to deal with this. Okay, so the vertex is the coordinate, right? That's either the lowest point or the highest point on the parabola. See here on this one where it's opening up, we have a minimum, so it's the lowest point on the graph. But when the parabola opens downward, we have a maximum, and so it's the highest point on the graph. So that's why we kind of have to define it that way, is because it's possible it's the lowest or the highest point. But either way, we're going to name it as a point, a coordinate. And so that coordinate here is going to be -1, +1. Okay, so the vertex is -1, +1, and that's because the vertex is right here. Okay, that's the vertex. The axis of symmetry is that vertical line that passes through the vertex. So it's the one that sort of cuts it in half. So I'm going to draw a little vertical line here. And so my axis of symmetry will be written as x equals -1. It's a line, so we have to describe it using an equation rather than just writing a number or something. So be very specific here, x equals -1. That's because every point on this line has an x value that's -1. Been a little while since we talked about how to write equations of vertical lines, so no worries if you kind of forgot about how to do that. So let's talk about the domain and range. Okay, so the domain is going to be the same for all parabolas. The only time in which that's going to be different is if you have some sort of restriction due to the context of the problem. Let's say you're talking about something that has to do with time and you don't want to include negative time or something like that, or if you just have some sort of arbitrary restriction on the domain and range. Otherwise, the x values will go from -infinity to infinity. There are no x values which will not give you an output. So we will say all real numbers. Okay, from -infinity to infinity. If you want to say something in terms of x, I guess you could say that x is all real numbers. We got a special symbol for that. You can write it either way. It looks like this. You got two vertical lines, and then you kind of make an R with it. So this symbol right here means all real numbers. But you don't have to write both. That's just what this thing means. If you like the symbol, you think it looks cool, you can use that. Or you can just write all real numbers. Now the range is the y values. So that is going to be a little bit different. Because not all the y values are accounted for, like y equals 0, for instance. You can see there's no points on the graph. Y equals -1, same deal here, no points on the graph. So there's no points below +1. So this is the lowest point on the graph, and there's no other coordinates below it. So the range will be written as y is greater than or equal to 1. Okay, so just to kind of highlight how I'm getting that, let me just, I'll try to make a little highlighter here. Say, okay, look, the domain goes, it encompasses all the x values, right? Let's see if I can make that a little straighter. There we go, that looks a little nicer. So it encompasses like all the x values, right? No matter what the x value is, you're going to have a y value associated with it. But as far as the y values are concerned, they are restricted, okay? So they cannot be below this line right here. There's no y values below this line, and that's why we're saying the range is greater than or equal to 1, because it's basically everything above 1, right? So the the range here is going to be everything that goes above 1. Now I'm going to, excuse me, delete these. These little yellow lines aren't going to make the final cut here on the notes, but I just wanted to kind of help you visualize where this is coming from. Okay, so that's the domain and range. Just a little reminder, because it's been a while since we talked about domain and range here. But let's look at it at the second one. So we're gonna find the same characteristics here: vertex, axis of symmetry, domain, range, all that good stuff. Let's see if I can copy these so I don't have to retype everything. Okay, so let's first talk about the vertex. So the vertex here is not -1, 1. What was the other one? The vertex here is, let's see, it's 3, 4, right here. Ooh, that's big. Okay, that might make it a little easier actually. So yeah, that's a big one. So vertex is not -1, 1. It is 3, 4. The axis of symmetry is going to be that that vertical line that passes through the vertex. Okay, so it's going to be right here. Draw some arrows. So that is the axis of symmetry, and so instead of being x equals -1, it's going to have the same x value as the vertex, which is 3, and you can see the line just goes through x equals 3. The domain is all real numbers again, okay, so that's not going to change. That's going to be true for all these abstract functions where there's no context, so you can just kind of copy and paste that answer to all the domain questions. But the range is going to be different. Oops. Oh gosh, now I'm screwing everything up over here. My bad. Okay, there we go. All right, so the range is going to be everything below y equals 4, not above. So like before we said everything was above this line, right? Let's make that a little easier to see. We said everything was above this line, right? So that's where the range is coming in. So it's everything above here. But here, it's going to only be the values below 4. Okay, so the range is going to be everything below 4. So let's see how we're going to write that. Instead of y being greater than equal to anything, it's going to be less than or equal to 4. Okay, so if you kind of put this together, notice, if you're trying to see, find some patterns in the values we're getting here, notice here that the vertex gives you an x and y value. The x value is going to be the same as what you get for the axis of symmetry, and the y value is going to be the number that you're going to put on the range. Okay, so those numbers should be the same. You got 3, 3, 4, 4. Just be careful with, if this is going to be less than or greater than, that sort of thing. Okay, so this is just a little bit of us trying to get used to these terms so you understand what each one of these terms mean. They're all important characteristics of the function, but what the real goal for today is going to be more so, hey, if I give you an equation, can you graph it? And so what we're going to look at is first, how does the a value affect the graph? And then we'll look at how the c value affects the graph. And we'll look at the b value next time. Let's take a look at this function. So you notice here I've got just ax squared. So I'm ignoring the bx, the plus bx plus c. I'm just going to assume that b and c are 0 here, and so I'm just going to delete those. So we've got this parent quadratic function, and what we want to do is examine what happens as the a value changes. So there's really two different things that the a value controls. The first thing that the a value controls is the width of the parabola. So notice what happens as I increase the value of a. As a gets bigger, notice that the shape of the parabola is getting thinner, it's getting narrower. And that's because what's happening here is we have a vertical stretch. We're basically stretching the parabola away from the x-axis. And as a gets smaller, it gets wider. Notice it's getting wider and wider until, what's going to happen when we get to 0? Oh, now it's just a blank line because it's just y equals 0, right? So it kind of flattens out, and then when we go to negative numbers, there it goes again. So it actually flips over the x-axis. So there's basically two things to note here. First of all, as the a value gets bigger, or I should say, as assuming a is positive, as that number gets bigger, you're going to have a narrower parabola. As it gets smaller, it'll be wider. Okay, and if it happens to be negative, you're going to flip. Okay, now I got to be careful about how I'm describing like bigger or smaller when it comes to the negatives, because look here, as I go further and further smaller here, it is making it more narrow. So the way I'm going to describe that is just basically the further away that the a value is from 0. So here, we can just let this kind of do its thing. So the further away that a is from 0, the narrower the parabola is going to be. The closer that this thing, when you start getting closer to 0 around here, the closer the value is to 0, the wider the parabola is going to be. And if you happen to be on the negative portion over here, if a is negative, it's going to be flipped over the x-axis. If it's positive, it'll be flipped. Well, there'll be no flip. It'll just stay above the x-axis. So just to kind of summarize that up, let's assume that a is positive, okay? And let's say it's smaller. So like the parent function, the sort of default value here for a is 1, okay? Now, if it's smaller than that, if it's like 0.5 or 1/2 or 1/3 or just any number that's between 0 and 1, then we will say that the function or the parabola is wider than the parent function. Now, as you get bigger, as a gets bigger than 1, okay, then compared to the original parent function, the parabola will be narrower. Okay, a little skinnier. So the only other thing to note here before we start looking at some examples is that if it's negative, if the a value is negative, then the function will be reflected over the x-axis. So just to be clear, there's some other terminology I want to bring up here. Okay, when we talk about whether it is wider or narrower, we are talking about a vertical stretch or a vertical compression. Now, I'll probably be pretty loose with these terms in Algebra 1, but as you get further into your math studies, you might want to be a little bit more technical about how you're saying this. But as we get wider, what's happening is we're actually experiencing what's called a vertical compression. Okay, and as the graph gets narrower, we are experiencing a vertical stretch. Let's see if I can, there we go. Okay, now when we're reflected, sometimes, reflected is really the more common, is really the more technical way to say that. Sometimes you'll see it say is like it's flipped. it's flipped over the x-axis, which is a little bit more, not so technical way of saying it, but what I really mean here is like what I wrote before, is that we have a reflection. So these are just different transformations that we can apply to the graph. We can either do, a compression, a stretch, or a reflection. So the stretch makes it narrower because you're stretching it away from the x-axis. A compression makes it wider because you're pushing all the points towards the x-axis. And the reflection just flips it over the x-axis. So, down here we're going to be comparing the graphs to the original graph. Okay, so what I'd like for us to do is really, let's graph it on the graphing calculator. We're just going to do like a quick sketch here. But the more important thing is I want you to be able to compare the graphs to the original function. So let me bring up a calculator too. Here it is. Oh, there it is. And we're going to put first just the parent function, y equals x squared. And just take a quick look at what that looks like. Okay, pretty basic equation. We've got the table already written on the first page here, right? We've got this. 1 squared is 1, 2 squared is 4, 3 squared is 9, so forth. And that graph is going to look basically the same on all these. So what I'm going to do is I'm going to actually zoom in here, and I'm going to just do a quick little sketch in yellow because I don't want it to be or maybe green, just to you can see it a little better. But I want to plot these points 0, 0, 1, 1, 2, 4, 3, 8, and that's probably pretty good. And then I'm going to connect the points, and then I'm just doing a rough sketch here. Don't worry if it's like not looking perfect. And I'm actually going to put this parabola, I'm going to copy and paste this on all these, just so that when we graph the new one, you'll see how it's changed. Okay. Otherwise, I think it's a little harder to tell what's going on if you don't actually have the parent function graphed on there as well. So see if I can make that fit. Okay. And then let's get this last one over there. And you probably can't see what I'm doing at the moment, but that's all right. Okay, so there's the parent function. Okay, and what we want to do is compare that to the new function. Okay, the new function in this case is going to be 3x squared. So I'm going to include that over here, and just so that I can visually see the difference, I'm going to change the thickness of the graph by going over here and just hitting enter. And that's you can see, make it like a darker line. So when I hit graph, you can see the darker line is the new one. So if we're just trying to describe what's happening here, we can basically be done here because we say, okay, well look, it's narrower. And that's because this number, this 3, is bigger than 1, which is kind of what we expected, right? So the way that the graph is going to look here, and you can, if you're not sure where, how I'm graphing these, I'm still using the table. We will get to a point where we don't need to use the table every time, but I can go to the table and plot some of these points out, and I should be using the y2 values. So notice that every value is the same, just multiplied by 3, and that's why we're having this vertical stretch, because all the points are being basically, all the y values being multiplied by 3, which sends them upwards. So the new graph is going to be 1 times 3 is 3. Oh, no, it doesn't like that. There we go. 1 times 3 is 3. Well, 0 times 3 is still 0. Oh, I don't want to be green. We're not going to be able to tell the difference. There we go. So we got 1 times 3 is 3. 0 times 3 is 0. What was that? 4 times 3 is 12. So that's going to be like way up here. And then that's as much as we can fit on there. So my graph, again, this is going to be a little sloppy because I'm using a mouse here, but it should look something like this. The point being is that it is narrower than the parent function. Okay, so I'm going to zoom out so I can kind of fit everything else back on here. And then, let's see, there we go. So if we want to describe really what's happening here, we're going to say that the graph, your g of x, which is the new one, is narrower than the original function f of x. And that's the proper way to describe the comparison here, where it says compare the graph to f of x equals x squared, which is the parent function. Well, the new one is narrower than the parent. So as you can imagine, you could probably guess what's going to happen over here. This is going to be wider. So let's see how that plays out on the calculator. So I'm going to go and delete the 3x squared, change that to 1/3 x squared. So 1/3 x squared, and as we can expect, it should be wider. So there's the parent, and there's the new one. And just as we expected, it should be wider. And that's because all the y values are being multiplied by 1/3. So it stands to reason that would happen. Okay. So I'm going to go ahead and plot this out now. 0 times 1/3 is 0. 1 times 1/3 is 1/3. 4 times 1/3 is 4/3, which is like 1.3. Okay, 8 times 1/3 is 8/3, which is like 2.67. Yeah, I think. All right. So I'm gonna go ahead and plot these on the other half, because remember these parabolas are symmetrical. Okay, so if you can get one half of the parabola, you can just kind of copy it on the other side. And then let's see here. 1/3. Okay, so we got that. Let's see. 4 squared would be 16. 16/3. Now we're kind of testing the limits of my ability here. It might be easier at this point if we want to get more detail. Just stop doing everything in my head. Just look at the table here. Okay, so we got so -3. Oh wait, hold up. Okay, I screwed something up here. Oh boy, I see what I did. Oh gosh. All right, so. All right, I do have one little mistake here. My bad, y'all. 3 squared is 9. It's not 8. I don't know what I was thinking. If you're like screaming at the video right now and being like, Mr. Schuler, what are you doing here? Okay, so we need to fix some stuff up. So this is going to take a second here. In fact, I'm going to pause the recording so you don't have to sit through it. But basically what I'm going to do is I'm going to fix these points so that they're actually 3, 9 instead of 3, 8. That's why I saw this point like that doesn't seem right. All right, I'm back. Okay, so I fixed it. You probably just saw a little bit of a jump here with these points going from 8 to 9. It's going to make this next point a little bit easier to graph, because instead of doing 8 divided by 3, we should be doing 9 divided by 3, which is, of course, 3. So our point here should actually be right here. So that's my bad, y'all. And then if I scroll down, I could get more points here if I really need to. Let's see, so like 4 is 16/3. Which 16/3 is about 5.3. So that's going to be the last one I plot here. I could probably fit more, but I think we kind of get the point. I don't want to spend too much time on, just plotting a million points here when really our goal needs to be able to compare the two graphs at this point, which I think we can do. So we're gonna basically answer this very similar to how we answered the last one, which is, in the last one we said that the new function is narrower than the old function. Well, that's how we're going to answer this one too. We're going to say that m of x, which is the name of this function, okay, so I'm just using the name that's given, is wider than f of x. All right, so let's get this over here because we're going to do number 5. Let's see if I can fit that on there. There we go. Okay, so for number 5, we've got, actually what we have here is we've got the same thing as number 3, except it's negative. So what we're going to see is that we actually get the exact same graph, except it's flipped over the x-axis. So let's see here. Let's go to y equals. I'm going to change the second equation to -3x squared. So what we're expecting here is a graph that's narrower, but also flipped over the x-axis because of the negative. So when I hit graph, there's the parent, and then the new one is exactly, it should be, yep, there we go. I forgot to make it bold, but I don't know if we really need to since it's on the other side. It's really easy to see which one's which, but just to make it, oh, you can't see what I'm doing. There we go. So yeah, I just went to y equals, I put in the 2 equations, and then I went to graph and took a look at it. So let's go ahead and graph this, and then we'll kind of move on here and see how C will affect the graph. But let's plot this new one. We've got a point at the origin. We've got to plot a point at 1, -3. because 1 times negative 3 is negative 3. 4 times negative 3 is negative 12, so we're already way off the grid. And that's because of how narrow this graph is. Oh, that was kind of ugly. Let's try that again. Really hard to draw with a mouse, I've noticed. All right, I don't know if it's going to get much better than that. There you go. Okay, so to describe the difference here, though, we're going to need to make two statements, okay, because we have to address the fact that it is wider. Okay, so n of x, it's narrower, is narrower than f of x. That's not m, it's n. N of x is narrower than f of x, and it's reflected over the x-axis. All right, so we do need to address both of those things when we're comparing the graphs. So that's pretty much it, okay? So if you are dealing with an a value that is not 1, so one that's different than the parent function, you are going to describe the difference as either being narrower, wider, or reflected. Okay, those are basically your three options. But let's go ahead and look to see what's going on with c. So we still got this a value moving around. So let me go ahead and stop that. I'm going to make a the same as the parent function, just 1. It'd be like if I just straight up deleted a. We really don't even need it anymore. But let's see what happens if I add a constant. Okay. So in here, basically what I'm doing is I'm going to be squaring the x values and then adding some number or subtracting. So if I add a number, so if it's 0, this is the default location is 0. Oh, let's get that to be exactly 0. Oh boy, c is 0. There we go. So at 0, the origin, the vertex is at the origin. And as I increase c, it's going to move up. And as I decrease c, it's going to move down. So what c ultimately controls is the y value of the vertex. Not only that, but it also controls the y-intercept. In fact, let me just stop it randomly. Boom. You'll see 3.11. Well, we've got our y-intercept is 3.11. So whatever the constant is, that will always be the y-intercept. So let's break that down. Notice here we've got a black parabola, a blue parabola, and a red parabola. The blue parabola has been shifted up 2 units, and the red parabola has been shifted down 2 units. So that blue parabola, assuming we know that the a value is just 1, we're just going to assume that, we have f of x equals x squared plus, and then it's been shifted up 2 units, so plus 2. The red one has been shifted down 2 units, so it would be f of x equals x squared minus 2. The black one is just the parent function, so we're just going to say f of x equals x squared. Now, just to further establish this, if your c value is positive, okay, so when I say c greater than 0, what I really mean is c is positive. Okay, so when c is positive, then the way you're going to describe the graph is that it's been shifted up. So when c is greater than 0, the graph is shifted up c units. So whatever the number that it happens to be. When c is negative, that means that c is less than 0. So when c is less than 0, we say c is negative. The graph is shifted down c units. When your b value is 0, then we've noticed that the vertex kind of stays on the y-axis, and next time we'll get into more like how to deal with when you have a b value that's not 0. But for today, the vertex is going to lie on that y-axis, and it's always going to be equal to the y-intercept, which is c. So the vertex, if you don't have a b value, and that's a really important if, is going to be 0, c. And the axis of symmetry, again, this is only true if b is 0, is x equals 0. So it's that y-axis. So that's just for today. Next time we'll get into like what happens if that isn't the case. But for today, that will stand. So let's look at these graphs down here. And we're doing kind of the same thing. We're going to compare the new graphs to the parent function. Oh, it looks like I already had something written there. Spoiler alert. All right. I'm going to take a minute, and maybe you've paused the video too, and just sketch out the parent function on all 4 of these graphs, because we really need it to be able to do a decent comparison here. So I'm going to do this not live. I'm just going to pause the video. Maybe you should do the same thing. All right, so I got the parent function down here, and now we want to graph x squared plus 5. So I thought I might do something a little bit different here. Instead of just like redrawing the whole thing, I want to show you exactly how it gets transformed. So I'm going to take this parent function, I'm going to copy and paste it. I'm going to change the color to red so you can see it's the new one. So like this is the original parent function, and then notice how the graph is plus, or the function is now plus 5. So according to what we talked about just a moment ago, that means that we need to shift the graph up 5 units. So I'm just going to literally take this and drag it up 5 units, and boom, and that's our new graph. And that should be how you describe the comparison as well, is that it's shifted up, that many units. So when I go down to describe down here, I'm going to say, well, what was this one called? G of x. So G of x is shifted 5 units up from the original f of x graph. So these names are just the names given to the functions. In the directions it said f of x was x squared. I don't know if you can see that. There we go. All right, well, let's take a look at number 8 here. Same thing, okay, same kind of problem, where we've got a function that is the parent quadratic function, but minus 3. So if we have a minus 3, that is going to shift our function down. So we're going to go down 3 units, down 1, 2, 3. Okay, notice this does not change like the overall width of the parabola, it just shifts it down. And so that's how we're going to describe the change here. So we're going to say this one's called m of x is shifted down 3 units from the parent function f of x. Now it's possible to have multiple transformations here. Oh wait, you can't really see that. Let me just scroll down so you can actually see what I'm writing. There we go. So it's possible to have multiple transformations, and we're going to see that in the next problem. So if we look at, let's see if I can get this to fit on here. I might have to zoom out a little bit just so I can get it to fit in the window here. No, that's still not. I might have to zoom out quite a bit. That's okay. We will get that in. There we go. Okay, so for number 9, we've got not only a shift down 4, but we also have to multiply the y values by 1/2, which is going to cause it to be a little bit wider. So I'm going to try to do the same thing I did with this one. So I'm going to highlight all this. I'm going to copy it. I'm going to paste it on there. I'm going to change it to red so I can see it's a new one. Okay, so here's the original function. Okay, first things first. Let's multiply the y values by 1/2. That's going to cause us to be a little wider. Now, I don't know if I'm going to be able to do this, and if I can't, okay, well, maybe I'm just going to give up on that guy. Let me try one more thing. All right, yeah, that didn't really work like I wanted it to, so I'm just going to redraw it. No big deal. Okay, so but I got to be careful here. Okay, so what I'm trying to apply 2 different transformations. Okay, so the first one is multiply the y values by 1/2, and then I'm going to shift down 4. So 0 times 1/2 is 0, minus 4 puts me right here. 1 times 1/2 is 1/2, so that would put me like right here, but then I got to shift down 4 units. So that's going to put me at negative 3.5, and that'll be true on either side. So number 4 is times 1/2 is 2, and then shift that down 4. 1, 2, 3, 4 puts you here. Now I do want to remind you that you have the ability to use calculators. So at the end of the day, like if this is when you have these multiple transformations, if it's just getting too complicated, don't feel bad about just going to y equals. typing your function in here, 1/2 x squared minus 4, and just look at the table. Well, here's the graph, but look at the table here. So see how it's wider, it's shifted down, we're getting there, but if you look at the table, that can also help you, if you're just really getting stuck here. Okay, that's not what I wanted. Now we're getting wild. All right, okay. So the next point, 9 divided by 2 would be 9/2. That's 4.5. Move that down 4, puts you at 0.5. So that's probably enough points. Looking at the calculator, I could do 4, 4. Might as well throw that on there because that's so easy to plot. But once you get, that many points, that's probably enough to get the general shape of the graph, which is what we're looking for. So as we finish graphing this, let's think about how we're going to describe the different transformations. Or how does this compare to the parent function? So this one has 2 different transformations. The first one being that it is wider, so we're going to say q of x is wider than f of x, and we'll say that q of x has been shifted down 4 units. Okay, so we have to make sure we describe both of those. We've got one last problem here, number 10, and then we're done for today. Let's get this calculator out the way. All right, so I'm going to just put this in here just so you can kind of see, but what you're probably going to notice right away, oops, didn't mean to delete the parent there, is that we're going to have 3 different transformations to apply. Now at this point, I would not recommend trying to do all this by hand, all these different transformations. If all we're trying to do is describe them, we can take a look at the graph, and it's pretty obvious what's going to happen here. We got a reflection because of that negative sign. It's going to be narrower because the a value is bigger than 1, or the absolute value is, rather. And then it's kind of shifted down 2 units. Okay, so I'm going to actually describe it first here. So I'm going to kind of shift gears from how I did the previous couple problems. And I'm going to just type out the transformation. So n of x is narrower than f of x. Okay, that's the first thing. Second thing is it's got reflected over the x-axis. And then the last and final thing is that it's shifted down 2 units. Okay, so you got to account for all 3 of the transformations. Can I make this fit on here nicely? That's good enough. And we can still graph it. When you get more than 2 transformations, it does get a little tricky making sure you're getting all the points in the right spot, which is why I usually defer to the table at this point. There's just no reason to kind of, oh wow, okay, I'm not sure what happened there. I lost my window. All right, sorry y'all. One of these days, I keep telling you I'm going to get better at this. It hasn't happened yet. So here I'm just going to, plot everything that I can realistically find. So, like for instance, 0, -2 is a point. There we go. And 1, -5 is a point. That might be all we can fit on here. Let's see, 2, -14 is already going to be way off the grid, so I'm not even going to bother. So our parabola is going to look like this. So it's good to be able to sketch these out, but you also want to be able to compare the graph transformationally to the parent function. So that's it for today. Oh, got a nice calculator on my face. That's it for today, y'all. Next time we'll look and see how B affects the graph as well. So just to kind of sum up here, we talked about the effects of A and C on the graph and how they transform the parent function. The A value will affect the graph in 2 ways. It will either make the graph narrower or wider, so it controls the width of the parabola. And then the second way it affects the graph is if it's negative, it flips it over the x-axis. So changes the width and changes whether or not it's opening up or down. We also looked at the effect of C on the graph, and we saw that C will control where the y-intercept is. In fact, C is the y-intercept, and it will shift the graph up or down depending on what you're adding. That's it for today. I'll see you guys next time. Have a great day.